Hello students, good morning to one and all. Myself Dr. Nazim Ahmed, Department of Chemistry. Welcome to this online class. Yesterday we discussed about some of the basic subtopics of stereochemistry. Followed by this session, I repeat once again. Stereochemistry is the branch of chemistry concerned with the 3D arrangements of atoms and molecules and the effect of this on chemical reaction. Look at these structures: linear, trigonal, bent or angular type, similarly tetrahedral, trigonal, bipyramidal, trigonal, pyramidal, and octahedral. Now, what is the concept behind that isomerism? Yesterday also we discussed the classifications. Now followed by in this session also I am repeating so that you get clear-cut idea. Berzelius coined the term isomerism. Look at the picture. He is Berzelius. Greek, that it is derived from the Greek isos, that equal to, that is means equal, mers, that is part, equal part. Isomerism, that means equal part. To describe the relationship between two clearly different compounds having the same elemental composition. Such pairs of compounds differ in their physical and chemical properties and are called isomers. Now look at the structure of ethanol and dimethyl ether. Now you find out the differences. Okay, CH3, CH2, OH. Okay, CH3, CH3, CH2, OH. Whereas here dimethyl ether, CH3O, CH3. Now the types of isomerism, as we discussed yesterday. Isomerism is broadly classified into two types. One is the structural and second one is the stereo. Structural, which having the 5 subdivisions, further 5 classifications based on chain, positional, functional, metamerism, tautomerism, and ring closure, ring chain. On the other hand, the stereoisomerism is further classified into two types. One is the geometrical isomerism and another one is the optical isomerism. Geometric isomer differ in their spatial arrangement about a double bond. Very important point, please remember. Geometric isomers differ in their spatial arrangement about a double bond, whereas on the other hand the optical isomers differ in the arrangement of atoms in 3D space, which create mirror images of each other. Which create mirror images of each other. Structural or constitutional isomerism, it's six types of signifying the main differences in the structural features of the isomers are. The first one is chain or skeletal or nuclear isomerism, followed by position, functional metamerism, tautomerism, and ring chain isomerism. Now look at this in the chain or skeletal nuclear isomerism. These have same molecular formula but different arrangement of carbon with carbon chain within the molecule. Look at this, the same molecular formula. It is C4H10. C4H10. How we are writing? 1, 2, 3, 4. Okay. N-butane, or we can write a 2-methyl propane isobutane. Here also 1, 2, 3, 4. Like that. So similarly, C5H12 also we can write a 2, 2 dimethyl propane and a 2-methyl butane isopentane. So these are the basic things. Position isomerism differ in the position of attached atoms or groups in position of multiple bonds, double bond or triple bonds. Look at this. Ortho dichlorobenzene, meta position, para position, is it not? So this is ortho, this is para, this is meta, this is para position, this is meta position. So you know all those things, just I am recalling you. Similarly, functional isomerism, these have molecular formula but different functional groups. Ethanol dimethyl ether, ethanoic acid, methyl methanoate. Similarly, acetone and propionaldehyde. Okay, from ketone to alcohol. This functional group is difference. Here also, ethanol, alcohol. Here ether. Here you find ethanol. Here ether. Likewise, here also ketone. Here you have aldehyde. So changes in the functional. Similarly, metamerism, these have different number of carbon atoms or alkyl groups on either side of a bifunctional group. Look at this so that you get clear idea. In isopropyl methyl ketone, similarly pentane 2-one, similarly pentane 3-one, different number of carbon atoms. Tautomerism, structural or constitutional isomers existing in easy and rapid equilibrium by migrating of an atom or group or tautomers. Keto-enol tautomerism, enol form, keto form, lactam form, lactim form. Look at amine, imine, amide, imide. So these are all the structural tautomerism. Look at the differences. Now come to the stereoisomerism. That is our topic. Isomers which have the same molecular formula but different in the manner their atoms or groups are arranged in the space are called stereoisomers. It is of two types. One is the conformational isomerism and second one is the configurational isomerism. Please remember the two things to be noted here. Same molecular formula but different in the manner their atoms or groups are arranged. The space are called stereoisomers. It is of two types. One is the conformational isomerism and other one is the configurational isomerism. What is conformational isomerism? The stereoisomers which can be interconverted rapidly at room temperature. What is the room temperature? You know. Yes, it will be around 24, 28. So, without breaking a covalent bond are called conformational isomers or conformers. The stereoisomerism which can be interconverted rapidly at room temperature without breaking a covalent bond are called conformational isomers. Because such isomers can be readily interconverted, they cannot separate it at normal conditions. Point to be noted. Because such isomers can be readily interconverted, they cannot be separate at normal condition. They cannot be separate at normal conditions. Now the second one is configurational isomerism. The stereoisomers which cannot be interconverted unless a covalent bond is broken are called configurational isomers. In the case of the first case, what we saw? Yes, without breaking covalent bond. Whereas here, which cannot be interconverted unless a covalent bond is broken are called configurational. The configurational isomerism is again of two types. One is the optical, that is enantiomerism, and the geometrical isomerism. Please make note of it. One is the enantiomers and second one is the what we call optical and geometrical isomerism. Optical isomerism or enantiomers, the stereoisomers which are related to each other as an object and it is non-superimposable mirror image. Yesterday we saw with various example what is meant by superimposable and a non-superimposable mirror image are called optical isomers or enantiomers. Greek enantian means opposite. The optical isomers can also rotate to the plane of polarized light to an equal degree but in opposite direction. The property of rotating plane of polarized light is known as optical activity. For example, molecular formula C3H6O3 represents two enantiomeric lactic acid as shown below. Plus lactic acid, minus lactic acid, rotates the plane polarized light towards right hand side. Towards right hand side. It is a clockwise direction. Clockwise direction. Rotates the plane polarized light towards the left hand side. It is anti-clockwise directions. Now in the case of geometrical isomerism, geometric isomers are the stereoisomers which differ in their spatial geometry due to restricted rotation across a double bond. Due to the double bond, there will be a restriction, it cannot be rotated. These isomers are called cis-trans isomers. For example, molecular formula C2H2Cl2, that is 1,2 dichloroethane, corresponds to geometric isomers are as follows. So this is the what we called cis. This also cis. So this is a trans. Okay, this is trans. Opposite directions. Types of optical activity. Dextrorotatory, levorotatory, DEXTRO, dextrorotatory and levorotatory. The symbol is plus or D. Similarly, minus symbol or L. Rotates the plane polarized light to the right hand side, that is the clockwise direction, whereas levorotatory rotates the plane polarized light to the left, that is anti-clockwise direction. As you know, simply it is given D or plus symbol, the levo is minus symbol, or sometimes in world version it's called as L hyphen, small l hyphen. Now what is optical activity? So a solution of the substance to be examined is placed inside the cell. So actually this is a polarimetry experiment. Now incident polarized light. Now here angle of rotation, transmitted light which is rotated. So this is the sample cell from which we are passing the incident polarized light, and this is the transmitted, okay, these lights, transmitted light. Now this is the polarimeter. Look at this. This is the, as we discussed, sample cell, and here you have one polarizer. So observe rotation from which we can see the observed rotation by alpha symbol. So plane is rotated. Plane is rotated. So this is the rotate to null from this analyzer. Rotate to null. This is the polarimeter experiment. Angle of rotation is the angle degree by which the analyzer is rotated to get maximum intensity of light. It depends on nature of substance, concentration of the solution, length of the polarimeter tube, wavelength of the incident, monochromatic light, temperature of the sample. So these depends on the factors, nature of the substance, concentration of the solution in grams per milliliter, length of the polarimeter tube, wavelength of the monochromatic light, temperature of the sample, and we saw these other things. And also we discussed yesterday the chirality, optical activity discovery. So these are the crystal of sodium ammonium tartrate. Chirality, an object which cannot be superimposed on its mirror image, is said to be chiral, and the property of non-superimposability is called chirality. Thus our hands are chiral. Thus our hands are chiral. Similarly, alphabets R, F, J are chiral, and A, M, O are achiral. Understand? Look at this. R, J, J, F, F are the chiral objects. Chiral objects. Achiral objects, same thing. A, you are writing here, that also A. M, it also shows M. O, O. Whereas F, exactly opposite. If you show right hand, it shows left hand. Okay. Molecular chirality and asymmetric carbon also discussed yesterday itself. Enantiomers also we saw. Next we pass on to very important topic is projection formulas of chiral molecules. Configuration of a chiral molecule is three-dimensional structure, and it is not very easy to depict on a paper having only two dimensions. We are writing in a blackboard or paper is only 2D, whereas 3D is very difficult to draw. To overcome this problem, the following 4 two-dimensional structures known as projections formulas. One is the Fisher projection, Newman projection, Sawhorse formula, flying wedge formula. Fisher projection. Look at this. Towards the viewer. First you draw rotation of a Fisher projection by an angle of 180 degree. Okay, 180 degree about the axis which is perpendicular to the plane of the paper. Use identical structure. However, similar rotation by an angle of 90 degrees produces non-identical structure. Non-identical structure. Whereas in the this is the Fisher projection. Whereas in the Newman projection, in Newman projection, the carbon atom away from the viewers is called rare carbon, and it and is represented by a circle. The carbon atom facing the viewer is called front carbon, and it represented the center of the above circle, which is shown by dotted lines. Okay, front carbon. The remaining bonds on each carbon are shown by small straight lines at angle 120 as follows. Bonds joined to front carbon intersect at the central dot. Okay. Bonds joined to rear carbon are shown as emanating from the circumference of the circle. Okay, so rear carbon. Now, the concept of Newman project for N-butane can be understood by the following drawings. So, look at this. This is the front carbon. This is the visible. This is the front carbon. Whereas this is the rear carbon. Understand? So, out of sight three groups emanating from circumferences. So this is 1, this is 2, this is 1 and this is 2. So this presentation is said to be Newman projection. Newman projection. Look at this staggered and eclipsed. Staggered and eclipsed. CH3 is very close to each other, is eclipse form, whereas this CH3 around 180 is said to be staggered form. Now the Sawhorse projection, the bond between two carbon atoms is shown by a longer diagonal line. The bond linking other substituents to these carbons are shown projecting above or below this line. Look at this, the presentations of Sawhorse projection. Due to free rotation along the center bond, two extreme conformations are possible: the staggered and the eclipsed. The staggered and the eclipsed. The fourth one is flying wedge formula. It is a 3D representation. The flying wedge formulas are of two enantiomeric lactic acid are shown below. Both structures are mirror images of each other. The dotted line and the bold line. The dotted line, the bold line shows the 3D, that is beyond the image. Next class we will pass on to discuss the conversion of Fisher projection into Sawhorse projection. So with that I conclude my class. So today we discuss the introduction part of isomerisms, classification, geometrical and optical isomerisms, and we saw the various things in which the important thing is a polarimeter, as well as we discuss the four formulas. Understand? So please go through the books which is available in our department library as well as college library. It is P.S. Kelsey Stereochemistry. Similarly, ELL. Before that, you go through some of the basic books like Basic Principles of Stereochemistry by Dr. P. Ramesh. Such basic book that will give the sound knowledge of the basic principles of stereochemistry is essentials for understanding the reaction mechanism, molecular rearrangements, stereo specific of enzymatic reactions, drug action, etc. Okay, thank you.